So we're going to find the area of part of a circle. Let's just temporarily pretend, well, no, let's call this r for radius, and then let's call this pi over 2. So this is 1/4 of the circle, right? So to figure out the area, you just do 1/4 of pi r squared. But I'd like to write this 1/4 in a strange way. So all the way around is 2 pi, right? And this part is pi over 2. So the fraction is pi over 2 out of the entire 2 pi. So this is the fraction 1/4. So is this. This is a crazy way to write 1/4, isn't it? But does it? Are you with it that it's 1/4? Okay, so I'm just taking 1/4 times pi r squared. So the reason I decided to do it that way is because then these pi's cancel. And we have 1/2 times pi over 2 times r squared. And notice that this angle right here corresponds to this angle right here. So that formula will work for any theta. So this is the formula for the area of a circle sector. Now don't let the fancy terminology circle sector throw you off. It's just part of a circle. So we're finding the area of part of this circle. That's called a circle sector. And the area is 1/2 theta times radius squared. See how that was working here? 1/2 times our theta times our radius squared. Okay, so in 10.3a we did the derivative of polar curves, and now today we're going to do integrals with polar curves. So here's the idea. We've got a graph, and maybe we want to find the area on this graph from an angle alpha. So we're going to rotate alpha, and then later we're going to rotate beta, and we're going to find all that area in there. Okay, if we were doing rectangular area, we would divvy this up into a bunch of rectangles. But we're not doing rectangular area today, we're doing polar area. So instead of divvying this up into a bunch of rectangles, we're going to divvy this up into a bunch of circle pieces. Okay, so here's one piece that kind of looks circular. See that piece of the circle? Here's another piece of the circle. Here's another piece, etc., etc. You get the idea? So when we were doing an area the first time, we divvied everything up into a bunch of rectangles and added them all up. Now today we're divvying them up into a bunch of pieces of circles and adding them up. Well, the formula for one of those pieces is 1/2 theta times r squared. So I guess I'm calling this theta. Thanks, Max. So we got 1/2 times theta times r squared. For this piece, and then 1/2 theta times r squared for this piece, and 1/2 theta times r squared for that piece, and we're going to add them all up. Okay, now, obviously, this isn't exactly right, is it? Because look at all this extra area I'm getting. Look at all this extra area I'm getting. Look at all that extra area I'm getting. So if I want to get a better approximation, I just do more pieces, right? Look at that. If I cut the pieces so that the theta is half as big as it was, I've got less extra area. So you know the punchline by now. We're going to go infinitely thin. So we're going to take 1/2 r squared d theta and add them all up from alpha to beta. So this is the formula for the area on a polar curve. So for example 1, to find the area of one petal of the polar curve r equals 2 times the sine of 3 theta. So we're going to go ahead and graph that and see what it looks like. So if you have your graphing calculator, go ahead and put it in polar mode and graph 2 times sine of 3 theta. And if you type things incorrectly, you should get something that looks like this. So they want the area of just one petal. So just this area or this area. It doesn't matter. They're all symmetric. Okay, so here's the idea. At this point, the r is maybe 2. And then at this point, the r is maybe 2.5, right? The r is how far you are from the origin. So at this point, then, the r is down to 1.5, and then now the r is 1. So when you get here, what is the r? 0. Okay, so the curve starts out with r being 0, and then r gets a little bigger, and then it comes back down, and then it ends up being r equal to 0. So if I want to know the thetas that are associated with this point and then that point, I need to figure out when the r is 0. So I'm going to set my r equation equal to 0. So I've got 2 times the sine of 3 theta equals 0. Divide both sides by 2. Sine of 3 theta equals 0. So we're trying to figure out when the sine of an angle is 0. That happens at 0 and pi and 2 pi, etc., etc., etc. And so we want to know when 3 theta equals that. Then you divide both sides by 3. So we just found out that to make the first petal, the theta was 0, and then it was 1, 2, 3, 4, 5, all the way up to, then when it got back here, the theta was pi over 3. Okay, so we're going to do our integral from 0 to pi over 3 to get just the first pedal. And just to drive that home, why don't you change your window on your graph to 0, and then pi over 3 on the thetas. Oh, and sure enough, when we do theta 0 to pi over 3, it does give us one pedal. All right, so you got the integral from 0 to pi over 3. And then the formula is 1/2 r squared d theta. So I just go ahead and type that in, and you should get 1.047. Yeah. Yeah, maybe I could use this integral by hand, figure it out, yeah. Okay, next one is find the area of the region that lies inside r equals 1. And outside r equals 1 minus cosine theta. Okay, so for r equals 1, I'm going to graph that without a calculator for practice. You put theta second and r first, which is kind of counterintuitive, right? And then for this graph, r has to be 1. So it could be pi over 2 with 1, or pi with 1, et cetera, et cetera, et cetera. So let's graph that. So rotate pi over 2, go out 1. Rotate pi, go out 1. Rotate this much, go out 1. What do we get? If the radius is always 1, it's a circle, right? That's what the definition of a circle, a constant radius no matter what angle. So there's r equals 1. Okay, then I'm going to graph 1 minus cosine theta. I could also do that one by hand, but I'm not going to today. So it goes back here to 2. There's what I'm getting. So they're asking for inside the circle, so in here, but outside the r equals 1 minus cosine theta. So this, that's what we're looking for, right? That half moon weird looking thing on the right there. Okay, so what we are going to do, just like we always do with polar, is we're going to divvy this up into parts of circles. So one of the slices is going to go to there. But then we don't want to count this, right? So it's going to be a part of a circle minus another part of a circle to get this. So it's going to be 1/2 r squared minus 1/2 r squared d theta. The part of the circle is 1/2 r squared d theta, and then minus the other 1/2 r squared d theta will give us this. Okay, now before I move on this problem, this kind of looks familiar, doesn't it? It kind of looks like this. What was this formula for? A 3D shape, the volume of it with a hole, right? The cantaloupe slice. Okay, so this is the volume of a rectangular curve rotated around a line with a hole in it. This is the area of a polar curve with a piece missing. They're almost identical. Swap out the half for the pi and they're the same formula. So don't let that mess with you. This is area, this is volume. Okay, we got to figure out what our bounds of integration are, right? Let's go back to this picture over here. Well, we're going to start, the shaded part starts here and then rotates to there. I mean, that really looks like negative pi over 2, doesn't it? It's a little bit dangerous to assume that, though. So let's plug negative pi over 2 into this. Well, what do you get? 1. Okay. Let's plug negative pi over 2 into this. Cosine of negative pi over 2 is 0. And then 1 minus 0 is 1. So they are intersecting at the point negative pi over 2, comma, or 1, comma, negative pi over 2. I just did that because some polar curves, even though it appears that that angle is pi over 2, maybe something got multiplied or something, and it's backwards. You know, could be up here but negative, or pi over 4 multiplied by 2 somewhere, leading to this. Yeah, you just have to think a little bit. And then this is 1 comma pi over 2. So the bounds of integration are negative pi over 2 to pi over 2. So then we got our big radius and our little radius. What's the big radius? It's not changing, right? At this point, it's 1. Here, it's still 1, because it has to do with the outer circle, right, where r is always 1. But the little radius, well, that's changing because it has to do with this curve. So it's going to be that, and then 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 that, and that, and that, and that. Okay, so the little r is this, the 1 minus cosine theta. Big R was 1, so we're doing integral from negative pi over 2 to pi over 2. I usually factor out the half 1 squared minus 1 minus cosine theta squared d theta. And then you can go ahead and function integrate that, and you should get 1.215. So that's polar area. Last week we did polar derivatives, right? How do you find the slope of a polar curve? You first have to convert it to parametric, right? Okay, so you take the r times the cosine theta, and that's x. And then you take the r times the sine of theta, and that's y. So then you got a formula for x and y, and then you do dy d theta over dx d theta, right? So that was derivatives with polar curves, and then this week was integrals with polar curves.